Hi everyone, this is Keshav Giri, application engineer for Mirabilis Design. In the previous video, we went through the implementation for the ARM Core Link CMN Mesh network using VisualSim. We talked about the different iterations of the CMN network and the library blocks available in VisualSim to be able to model the CMN mesh. And in this video, we will take a look at a 4x4 mesh example for a CMN Cyprus network. So first, looking at the block diagram for the mesh itself, this is a 4x4 mesh with 16 router nodes. And we have multiple HNPs, HNS, system level cache implementation, the super home node, the HND, HNI. We have memory devices in the form of the SPSX and the SNFs. We have CAL devices aggregating requests from RNF devices. And we also have RNI and RND nodes. So taking this block diagram and replicating it in VisualSim, this is what it is going to look like. So we have the 16 router nodes present in a 4x4 mesh. And we have the library implementations for each of the interface blocks. And we have recreated the configuration present in the block diagram. So we can see we have the super home node. We have the CCG devices interfacing with CXL. We have the HMP interfacing with PCIe. We have the HNI interfacing with an ACE bus. We have 18 request nodes in this system in total. We also have the CAL, which performs the aggregation for multiple RNFs. And we also have memory devices, the form of SPSX connected to a DRAM device and two SNF devices. So the configuration has been mapped from an ARM Socrates block diagram into VisualSim. The requested devices are connected to cores in this example, and these cores are traffic-based. And these cores can be replaced by actual processor cores to simulate the core execution by using either trace files or workloads. We have the PCIe 6, the CXL 3.0, and the AMBA ACE buses used to interface with the HNP, CCG, and HNI respectively. The HNS is implemented using the HNF library block with the addition of an external system address map. Since the HNF implementation will point to a specific memory device in the case of a cache miss, we have an external system address map connected to it to be able to implement the HNS or the super home, which takes care of the address ranges and mapping the request to a particular home device. So there are 19 requester nodes in total in this architecture. We have 4 Cal2 devices present, which are aggregating requests from multiple RNs. There are 5 PCIe interfaces, 2 CXL interfaces, and 3 AMBA ACE interfaces. There is one system level cache in the form of an HNS, which also can be expanded to multiple system level caches. There are 3 memory devices in total. There are 2 SNFs and 1 SBSX. All of them are connected to DDR5 memory. The clock speeds, the flit sizes, the buffer sizes for all of the devices present in the mesh network are can be configured by changing the individual block parameters. We can also set the memory sizes, the clock speed, and the device type for the slave memory device. In this example, each RN device has an individual system address map attached to the output. So whenever a request is created and sent out from the RN device, it looks up to the system address map present and selects the home device to which this request has to be routed. If in the case that the home device is not mapped for a specific address, that is, the address range has not been defined in the system address map, this request will be routed based on the global system address map defined in the core link setup or the CMN setup block, which is over here. So if the address range misses in the system address map lookup, it will look up to the global system address map defined in the core link setup block over here. The HNS has its own system address map to route requests in the case that there is a cache miss. So now let us take a look at the different interface connections as part of this example. So the HNP device is used to interface with the PCIe 6 bus. The PCIe uses an RNI for outgoing requests and a HNP for incoming requests. Both the requester and home nodes are connected across the PCIe bus. So the PCIe core is generating requests and the PCIe external is acting as a home node. And the PCIe itself can be fully configured through a set of parameters. So you'll be able to set the buffer sizes, the flit size, the number of lanes in the bus, and we can enable or disable flow control on both sides, the master and the slave side. Showing you an example. So we have 4 ports as part of the PCI interface block. So the home node input and output are going to be connected to the HNP, and the requester node input and output are connected to an RNI. So all these requests are going to flow through the PCIe bus, and based on whether it is an incoming request or outgoing request, it will be routed to the appropriate device, either the core or the PCIe external. Similarly, we have the CXL 3.0 implementation. So the CXL interface uses a CCG to connect to the mesh network. And in this case, the CCG can act as both the requester and home node. So the CXL interface does not require 2 separate devices to be connected to the mesh network. The CXL 3.0 can also be configured in a similar way. The buffer sizes, flow control, the link speed in GTPS, overhead cycles for each stage, individual stage cycle delays, the clock speed for the CXL, and the total number of lanes in the CXL can be configured. We also have an interface to the AMBA ACE bus using the HNI, and the HNI acts as a home node only. So we can see that similar to the other buses, we can also configure the bus configuration for the AMBA ACE. Now, taking in this mesh network, let us look at the kind of statistics we can generate through a simulation in VisualSim. So in this configuration, the first thing we have to look at is the top level parameters that are defined in the model. So if we zoom in here, we can see that as part of the architecture definition, we have these top level parameters where we are setting the simulation time, the frequency for all the router devices, the device frequency for the memories, for the requester nodes, the time period in which the traffic generators are going to be generating requests, which in this example is 1 request every microsecond, the overall address range in which the requester nodes are going to be generating requests, and the flit sizes for all the devices present in the mesh network. So in this configuration, all the devices, the router, the memories, and the requester nodes, the base configuration are all going to run at 2000 megahertz. The device flit sizes for all the CMN interface devices is set to 32. The simulation time is set to 1 millisecond, with all the 19 requester nodes generating traffic at a rate of 1 microsecond. And in this example, the requests are generated with randomized addresses that fall in this address range defined at the top level. So let us take a look at the kind of results that can be extracted from this model using VisualSim. The first graph that we are looking at is the request completion latency at the requester nodes. So we can see the completion time for each request that flows out of RNI2, which is this device over here, using this plotter over here, which is available in VisualSim under the results library. So we can see across the simulation run, where the simulation time is set to 1 millisecond, we can see the packet return latency for each request that flows out of the RNI. The next statistic that we are looking at is the per access throughput for each requester node present in the mesh in bytes per second. So the per access throughput is calculated as the request size for that request in bytes divided by the latency for all the flits to return back to the requester. You'll also be able to see the average throughput in bytes per second for each requester node present in the mesh, where the average throughput is calculated as the total number of bytes that have been sent back to that requester node divided by the current simulation timestamp. And we can see that if we zoom into the output graph, we'll be able to see the overall average throughput for each requester device at a granular level. The next statistic that we are looking at is the throughput at the HNS or the superhome node, the system level cache slice in bytes per second. And for the cache slice present within the HNS, we'll also be able to see cache statistics like the hit ratio, the miss ratio, the total number of requests, the total bandwidth, which is present here, the total MBs, and the total number of read requests, write requests, and the individual read and write bandwidth. And for the memory devices present in the mesh, we'll be able to see similar statistics, the total number of requests, the total bandwidth, individual count for the read requests and write requests. And we'll also be able to see the memory delay, the minimum, maximum, mean, and standard deviation values for a request to be completed at that memory device. And at the end of the simulation, we'll also be able to see aggregated latency statistics for each individual RN device and the buffer occupancy, maximum buffer occupancy statistics for each router device present in the mesh. So with regards to the latency, we'll be able to see the maximum, minimum, and mean network and end-to-end latency for each requester device, and the maximum buffer occupancy at each router at each directional port, north, south, east, and west. And with regards to the buses present in the mesh network, we'll be able to see bus statistics. So we'll be able to see total bandwidth, transmit bandwidth, receive bandwidth. With regards to the CXL, we'll also be able to see packing efficiency from master to slave and also from slave to master. And for the ACE bus, we can also see the total number of requests entered and exited, the delay, and the bus occupancy. Now, to perform trade-off analysis, let us make a few changes to the base configuration and see how that affects the results at the end of the simulation. So if we see here, we have changed the frequencies for the individual devices. So previously, all these devices were running at a clock speed of 2000 megahertz, which has now been changed. All of them are running at a faster clock rate. The device flip size has also been increased from 32 to 64, while the simulation time, the traffic rate, and the address range are not changed. So let us do a comparison between the results from the base configuration and this new configuration. So the first comparison is based on the per access throughput, and we can see that the per access throughput has increased in the case of the new configuration, where we have increased the flit size and the clock speeds for the individual devices. You can also see that the average throughput per requested device has increased, where previously it was at this level, and now all these devices have a higher average throughput. You can also see that the superhome node cache slice throughput has increased at the end of the simulation. Next, let us compare the end-to-end and network latency. So we can see that the mean end-to-end latency and the mean network latency have dropped for the request completion at all the RN devices. So through this kind of trade-off analysis, we'll be able to make configuration changes system-wide and also at each individual component present in the mesh network. And based on this trade-off analysis, we'll be able to zone in onto the optimal mesh configuration for the final implementation. Now, VisualSim has functionality called the post processor, which lets you run regression on your models. So let us take a look at that. So by choosing the post processor on the tool menu, we'll be able to configure a specific model. And in the model configuration, we will see all the top level parameters defined. And for each of these top level parameters, we can assign a range of values and the step it should take between these values. So for this example, we are varying the device flit size from 16 bytes to 64 bytes with a step of 16 bytes. And we'll be able to select which plots we would like to save and compare. So for this example, we are going to save and compare the mean network latency, mean end-to-end latency, the individual device latencies, and the throughput. So on selecting this post-processor configuration, a batch processing script will be generated in the model directory. So there are two choices here. We can either do a simulation batch run, which will run all of these configurations on a single thread, or we can choose the thread batch run, which will run batch processing on multiple threads. So on completion of the post-processor runs, all these configuration results will be stored in a directory that is created in the same location as the model. And this folder will contain a plot index file. So we can choose the plot index file. So we can see here. And it will list all the configurations that we have created. So we can choose all the traces that we would like to compare, and we can select a plot using which we are going to compare these configurations. So we can see here that instantly will be able to compare the mean network latency across all these configurations. And just based off of this view, we can say that configuration 1, the lowest flit size, 16, is not optimal as it provides the maximum latencies. And we can see that the other configurations provide lower latencies. So using these comparisons, we can choose the optimal configuration and select that for the final implementation of the CMN mesh network. So this has been me, Keshav Giri, application engineer for Mirabilis Design, presenting CMN mesh networks in VisualSim. Thank you.